In this video, we're going to be covering section 5.4, and we're going to be graphing the remaining 4 trig functions, namely tangent, cotangent, secant, and cosecant. And I want us to kind of start off in a similar fashion. I want us to just begin by plotting some values. And before we can plot those values, let's go ahead and find the corresponding y values in these spots right here. Let's start off with some of the easier ones, okay? I'm going to make us, instead of actually going over to our unit circle, I'm just going to make us one, because a lot of the points that we're going to need are just going to be the ones on the axes. Won't be all of them, but many of them. And so we know, for instance, up here that this would be what x equals 0, y equals 1. This one here would be 0 comma minus 1. We have 1 comma 0 and a minus 1 comma 0. There we go. And I'm also going to go in and just label that this is 0 radians. This is going to be pi radians here. So up top, we'd have pi over 2 radians, and then 3 pi over 2 radians here at the very bottom. Okay. All right. Well, let's begin with, I suppose, 0. Okay. So you might remember that tangent of theta is equal to y over x, where y and x are the y and x values from the points on the unit circle. So tangent of 0, we're going to want to do 0 over 1, right? Or y would be 0, or x would be 1. So 0 divided by 1 is actually 0. Well, let's go over to the next easy one. Let's come over here to pi over 2. So if we try this one out now, it would be 1 over 0. And you might remember when we have that division by 0, this is undefined. So is what I'm going to do here is I'm going to write in a u here for undefined. Or maybe I can fit in at least u and d. Okay. And so maybe we'll just say up here u. When we say u and d, we just mean undefined here. All right. Then if we go over to pi, the next easy one, we should have x or y over x. So the y is 0, the x is 1. So this one here is going to be 0. Okay. And 3 pi over 2, coming back over to here, that'll be minus 1 over 0. So we're undefined again. Let's also check minus pi over 2. So minus pi over 2 would just be rotating from here to here. So it's using the same location as 3 pi over 2. So again, we'll have minus 1 over 0, and this will be undefined here. All right, so all we have left are the minus pi over 4, 3 pi over 4, and so on. And so what I'm going to do is I'm going to move this out of our way, and then we'll go look at the real unit circle here. And by real unit circle, I just mean our one that has a little more detail. Okay. So if I go over here, I'm going to have us start off by looking at pi over 4. Let me just scoot this over. So you'll notice that pi over 4, both the y and the x are the same. So if we do y over x here, we're just going to get 1. If you divide something by itself, you get 1. Okay. So I'm going to go fill that in over here. This will be 1. Okay. If we go over to 3 pi over 4, let's take a look at that. So 3 pi over 4 this time is over here. If you do y over x here, they are the same two numbers other than one is negative. So this one will be -1 if we do y over x. And if you check 5 pi over 4, they'll both be negative, but the same number. And if you do a negative divided by a negative, you get a positive. So this one comes out to be 1. Okay. And if we were to go and check it, which we don't need to here, although wouldn't be a bad idea to do, this should be -1. So before, when we were working with sine and cosine, when we were looking at our quarter points, they were always 0, 1, or -1. And you can see something very similar is happening here for tangent. Um, these are indeed the quarter points. But there is going to be a very big difference in their shape. Okay. So what I want us to do is start off just by labeling our axes here. So let's maybe say that this right here is going to be pi over 4. And then pi over 2. And then 3 pi over 4. And then pi. And 5 pi over 4. And then after that, we should have 6 pi over 4, which is 3 pi over 2. And then I want to go in this other direction here, and we'll have a minus pi over 4. And what else? A minus pi over 2. Okay. So we don't really know why yet, but at all those spots where it says undefined, those are actually going to be the location of vertical asymptotes. Now, I want you to also notice how far apart these vertical asymptotes are. They're actually all pi units apart, which is exactly the period of tangent. So, right, tangent's pattern is going to repeat every pi units. Okay. And again, this is, of course, assuming that we have no transformation done here. Now, we could also go in and we could fill in these zeros, the middle here's. Okay. And I do need a 1 and -1 on my y-axis. There we go. So now if I fill in the remaining 1s and -1s, just looks something like this. And if we want to, we can actually start connecting these. If we were to do so far, it actually will have a little bit of curvature like this. And now I've already said that these are asymptotes here, but I want to think about why we might have an asymptote here at pi over 2. So if we go back over to this unit circle, as we start moving along in this direction, getting closer and closer to pi over 2, is what's happening is what's on top is getting closer and closer to 1, and what's on bottom is getting closer and closer to 0. So you're essentially taking things close to 1, and then you're dividing them by very, very small numbers, which will give you very, very large numbers. Okay. And in fact, the closer we get to pi over 2 here, the closer this gets to 0, making the numbers closer and close. Well, it's going to mean that those outputs are going to go off to infinity. Okay. So when we go to look at our graph over here, at these asymptotes, is what's happening is it should look something like this. I don't want that to look like a line. I want it to have some curvature to it. Okay. And so it looks something like this. Okay. And this just keeps repeating over and over and over again. What you're looking at here are two periods of tangent of theta. Now, if I were to think about what I consider the parent function to be, I always think about this part right here as my parent function. This is going to be the part that I'm going to think about shifting left and right and up and down and compressing and stretching. So let's just first note now that the period, which we've already said is pi. Okay. The range. So the range, that's the y values that are covered here. And because of these two vertical asymptotes, these vertical asymptotes we can see that it goes all the way up to positive infinity, all the way down to minus infinity. So our range is all real numbers, or an interval notation minus infinity to infinity. Something a little less obvious. You do not need to memorize this by any means, but we could also include the domain here. Okay. And if we were to include the domain, it's going to be a little bit tricky to write. Right? So if we were to try to write in that domain, here's how we'd have to do it. We'd need a bracket, and we'd want to say x is an element of the real numbers. Okay. So all that's saying so far is we're going to allow, and actually I'm writing in x, but our input variable is actually theta. I'm going to switch it to a theta. Okay. So theta is an element of the real numbers. And then that vertical bar I just put in there means such that. And so we're going to want theta to be equal to anything other than those values where we have the vertical asymptotes. Those are not part of the domain. So we want theta to not be equal to any odd numbers times pi over 2. You'll notice that we have minus pi over 2, pi over 2, 3 pi over 2. The next one will be 5 pi over 2, then 7 pi over 2. So yeah, we just want to exclude all of the odd multiples of pi over 2. And this is saying just where k is some integer. Okay. And so you might be seeing now why I'm saying you don't need to bother remembering how to write this. It's kind of complicated. Yep. All right. Well, let's go down and look at the graph of cotangent and see how that compares. And then we'll get a chance to try to graph these. Okay. So cotangent is going to be very similar. It might be nice instead to have this picture here again. I'm going to copy this over and we'll take a look. Let's again start off with those easy points. Or actually, there's a better way to do this. Cotangent is the reciprocal of tangent. So we could actually just do 1 divided by the numbers we see up here. With one exception, actually. So maybe I should just leave. Um, so is what I was trying to do is I was going to copy this again and bring it back down. I decided it is helpful. Okay. So for the cases where it does say undefined for tangent, we're not exactly going to be able to use the fact that they're reciprocals by looking at that, but everything else will be fine. For instance, at minus pi over 4, tangent is minus 1. Well, then that means cotangent would be 1 divided by -1, which is still -1. So if I scoot down here, is what I'm going to put in here, is this is still -1. Let me write it in here. Now, let's look for theta equals 0 at tangent. If we do that, we can see that tangent at 0 is 0. Okay. So if you do 1 over 0, we're going to get undefined. Okay. So this will be u and d. If we go to look at tangent of pi over 4, it's 1. So if you do 1 divided by 1, you get 1. And again, I'm doing 1 divided by 1 because 1 over tangent is cotangent. So I'm going to go over there and fill that in. So we have a 1 here. Okay. At pi over 2, let's see what tangent was at pi over 2. We had a vertical asymptote. Okay. So we need to kind of figure out what's going on here at these at minus pi over 2 and pi over 2. Okay. So again, do remember that cotangent, just like tangent, can be rewritten using x and y. So it's x over y now. So if we go to minus pi over 2, that would be right here. So if you do x divided by y, you'll get 0 over -1, which is just 0. And if we look at pi over 2, we're going to have almost the exact same thing happen. So this angle here. If you do x divided by y, you're going to get 0 divided by 1, which is 0. And now the pattern's just going to repeat. This is going to go -1, undefined. And then, let's see, 1 and then 0. All right. And you can double check some of those. Like, for instance, the 3 pi over 2. If we do x over y, we get 0 over -1, which is 0. And if we check out what tangent of pi was, it better have been 0. And it was. 1 over 0 will result in this being undefined. So we filled that out. Let's go ahead and try to make a sketch of this one here too. It's going to look very, very similar to tangent. And we'll learn how to, we don't know yet, but we'll be able to compute these values that go on the x-axis, just like we did with sine and cosine. The primary difference here is the period's different. So once again, at the undefineds, we're going to put in or some dotted lines to just let us know that there are some vertical asymptotes there. So we have 0. What else do we have at pi? There we go. And then let's plot the values we have. So we have 0. We have -1. So I need to label my y-axis. I need a 1 and a -1. There we go. So at minus pi over 4, y should be -1. There we go. At pi over 4, y should be equal to 1. At pi over 2, y should be equal to 0. At 3 pi over 4, it should be -1. 5 pi over 4, it's back up to 1. 3 pi over 2, back down to 0. There we go. So again, you can only see 2 asymptotes this time, but notice again, they're still pi units apart, which is the period of cotangent. So this Again, pattern repeats every pi units. And we're going to get the same shape here. There we go. And while I'm not going to finish the shape over here on the left, I can put half of it. Okay. And it looks like I have enough for half over here as well. So we technically do have full 2 periods, but you're only actually seeing that shape once. And by that shape, I mean what you see there from 0 to pi. So we can go in and we can fill in the period, the range, the domain here. So again, the period we said was pi. The range is still all real numbers. We have those vertical asymptotes. And then lastly, the domain. So this one's a little bit easier to write than the last one. You can see that, you can see 2 of our asymptotes are at multiples of pi. Well, it ends up all of them for cotangent are at multiples of pi. So we only need to exclude those multiples of pi. So if we were to write in our domain, again, you don't need to remember this, but this is how we would formally write it. So that E thing means in. So I'm saying X is in the set of real numbers such that is what this vertical bar means. And I want to say that I do not want X to be a multiple of pi. Those are the values we're excluding from our domain. There we go. All right. So is what I want us to do now is just kind of review what A, B, C, and D tell us. They tell us almost the exact same things for tangent and cotangent that they told us for sine and cosine. So let's go ahead and scoot down. So transformations with graphs of tangent and cotangent. So the absolute value of A before, we were calling this the amplitude because it was essentially the amplitude tells us how far we go from the center of the wave to the top or the center of the wave to the bottom. Okay. But we're not working with waves anymore when we're working with tangent. So this absolute value of A is just simply the vertical stretch or compression. And so let's go ahead and we will write that in here. Let's say or. Okay. So it's just doing what you're used to it doing. You have that number in front of a function. If it's a number bigger than 1, it's going to make that function um, have more extreme y values. And if it's smaller than 1, those y values will become less extreme. And is what I mean by this is if you have a 2 in front of a function, it's going to double the height. Okay. And if you have a 1/2 in front, it's going to halve the height of whatever that function is. Now this right here, pi over b, should look similar. This is the period. So when we were working with sine and cosine, we were doing 2 pi over b because the period for sine and cosine with no transformations done is 2 pi. And that b there causes a horizontal stretch or compression. So in other words, if we had a 2 in place of b, it would compress our graph by a factor of 2. So rather than completing a period in pi units, it would now be pi over 2 units. Right? And then D here, we have our vertical shift. That just really means the same thing. C also means the same thing. We will not call it the phase shift anymore. Again, phase shift is a terminology that has to do with waves, and we're just simply not working with waves here. So this is just going to be your horizontal shift. And lastly, spacing. And spacing is also found the same way. It's the period over 4. Okay. So we're going to use all this information here and the parent functions up here to try to graph one of these. So it says graph at least 2 periods of the following trig functions, and we have y equals 3 tangent of 1/4 x. Okay. So let's start off with that a value. Okay, so a here is equal to 3. This is our vertical stretch. And notice that there's no vertical shift anywhere. We don't have like plus some number at the end. So if we do go back and look at the parent functions, we only really put 1 and -1 on the axes. But because of that 3, instead of 1 and -1, I'm going to put -3 and 3. So we again have a stretch by a factor of 3. There we go. So the y-axis is already set up. What else do we have on our list here? We have the period that we want to find. Let's go ahead and find the period. So the period should be equal to not 2 pi over b anymore, but pi over b. So I have this pi over 1/4. And if we simplify that, right, we're dividing by a fraction. So you're going to flip that fraction over and multiply. This is just going to be 4 pi. So that's our period. And so that means for our spacing, we just want to take the period and divide by 4. There's the period, divide by 4, and we get pi. So it's pretty nice spacing. When we talked about our horizontal shift, you might remember that, well, we need x minus something to create a horizontal shift. And we're not subtracting or adding anything to this x in here. So there is no horizontal shift. So that's convenient. So normally the first place I start is by putting a tick mark wherever the horizontal shift is. Okay, since we don't have one, I guess I'm not going to put a tick mark at the origin. There's already one kind of here in some sense. But I do want to add pi's to that and subtract pi's from that to get my remaining points on the x-axis here. So I'm going to, again, start counting by pi's. There we go. So let's just first remember where the asymptotes go. Okay. So the asymptotes, you can see on, well, for tangent and cotangent, they are 2 quarter points from the middle of the wave. Okay. So I'm going to put my first 2 asymptotes as being 2 quarter points from the middle. So if we come down here, is what that's going to look like. That's 2/4 points to the right. This is 2/4 points to the left. And you can see that these are really 4/4 points apart, or they're 1 period apart, which is 4 pi in this case. So if we went another 4 pi over, that would actually get us to 6 pi. And so in the very middle of your asymptotes is going to be the middle of our tangent function. So I'm going to just go like that. Okay. And then if you go 1 unit to the right of the middle, tangent goes upward. And rather than going to 1 at this quarter point, it goes to 3 because we had that vertical stretch by a factor of 3. And instead of going down to -1 here, it's going to go down to -3. And we're just going to do the same exact thing over here at 5 pi and 3 pi. And we'll just go ahead and finish this by connecting with something that looks like the shape of tangent. And right there is our final graph. This is 2 full periods that we're looking at here. All right, so let's go over to and try one here for cotangent. Here we go. So I want to notice a few things. One is that we have this reflection because there's this negative here. So I just want to put in here, well, we're going to have a vertical reflection. We're also going to have a vertical stretch by 3/2. And notice again, there's no vertical shift here. So rather than going up to 1 down to -1 on my y-axis, I'm just going to go 3/2 and -3/2. There we go. So we have our 3/2 and -3/2 sketched in there. Let's start thinking about some of our other transformations. Before we try to find the horizontal shift and say the period, let's do a little bit of factoring. So if we want to factor this, we could factor out a 2, and that's going to leave us with pi over 4 here. Okay. And I want to remind you all how I got this pi over 4. So to get that, I just took this pi over 2 and I divided it by what I needed to factor out, which was a 2. And so if you try to simplify that, you could rewrite the 2 as 2 over 1, and then you'll flip and multiply by that bottom fraction, and we'll wind up with a pi over 4. And you can check if you were to distribute this 2 back through, we'll wind up what we started with, which is a 2x plus pi over 2 on the inside of that cotangent. Right? So then next, now let's go ahead and find that period. So the period is equal to, again, not 2 pi over b, but the period for tangent and cotangent is just pi, so we'll do pi over b. And our b here happens to be 2, right? That number right here is our b. This also means that we're going to need to find the spacing that we're going to use and the horizontal shift. So let's find our spacing. Our spacing should just be the period over 4. And if you simplify that, you're going to get a pi over 8. And then lastly, our horizontal shift. And so this should be to the left pi over 4 units. I'm just going to write minus pi over 4. So again, this is what I like to start with, is the horizontal shift or the phase shift if we're talking about sine and cosine. So I'm going to mark on here first where minus pi over 4 is. So let's maybe go and mark that here. Maybe right here. And then we want to start counting by pi over 8. And notice pi over 8 is half of minus pi over 4. So my minus pi over 8 should go right here. If I add another pi over 8, I'll end up at x equals 0. If I add another pi over 8, I'll wind up right here. And another pi over 8, I'll end up with pi over 4. Another pi over 8, we'll get 3 pi over 8. And then 4 pi over 8 is pi over 2. All right. And what after that? Then 5 pi over 8. And I'll end on this side at least with a 3 pi over 4. So that would have been 6 pi over 8, which simplifies to 3 pi over 4. And on this other side, I'm going to add in 2 more tick marks. There we go. So for cotangent is what I like to always think about is what happens to, where's it at here? Yeah, what happens to this very first vertical asymptote? Where is x equals 0 going to get moved to? Okay. So this part that I've highlighted here, this vertical asymptote, it should be getting shifted over by pi over 4 units, right? We had that horizontal shift by minus pi over 4. So I'm going to have a vertical asymptote right here. Okay. Again, it would have been at x equals 0 if it wasn't for the horizontal shift. There we go. Similarly to the other ones that we've done, if you just count to the right 4 quarter points, you should end up at the next vertical asymptote, or if you just add the period to this. And so what that would put us right here. The period in this case was pi over 2. And if you add pi over 2 to minus pi over 4, you'll get a positive pi over 4. Again, I usually just count the number of tick marks in between. Okay. You can see that in between these two sets of asymptotes, or two pairs of asymptotes, there are the same number of tick marks in between. Okay. All right, and so let's go ahead and now try to fill some of this in. So let's again use this as our starting point. That's where we moved x equals 0 to. We moved it to right here. Okay. So I'm going up to here. After this very first asymptote, you can see that the next quarter point, it was at 1. Okay. and then we had 0, and then minus 1. Well, for us, this is going to change a little bit because we had that 3/2 in the front. So instead, it's going to look something like this. And I'm actually going to make a slight error here, and I'll correct it in a minute. But we'll have this one here. That's the first quarter point after this first vertical asymptote. And then we'll be in the middle, and then we'll be down to minus 1. Okay. Now, this is what would happen if there were no vertical reflection. But we have this reflection across the x-axis thanks to that negative we had in front of the cotangent. So rather than being at 3/2 here, I should actually be at minus 3/2. Okay. This won't affect this one, because if you take 0 and multiply it by minus 1, you still get 0. But it will affect this one. This one was minus 3/2, so now it's going to be positive 3/2. Okay. And if I go ahead and connect the dots, go. And so what you might be seeing here now is this looks a lot like tangent. Okay. So it ends up that any sine function can be rewritten as a cosine function. And any tangent function can be rewritten as a cotangent function. Now, if I go into this next set here, I should follow the exact same pattern. So 0 in the middle, 3/2 over here, minus 3/2 over here, and again, the same shape. That right there is our graph of cotangent. And so is what I'll have us do in our next example is we're going to try to come up with the equation of the tangent function that's been plotted here. Okay. So there's a few things to note here. It is kind of hard to see, but this actually says minus 3 pi over 2. This says 3 pi over 2, and this says 9 pi over 2. So for one here, if we want to find the period, we could just look from here to here. What is that distance? Okay. So the period, if I want to find this distance, well, I could just do my 3 pi over 2 plus another 3 pi over 2. Because, right, we have 3 pi over 2 units this way plus 3 pi over 2 units this way to make that full period there. And so that's just going to give us a 3 pi. And you might be wondering, well, why was that helpful to find the period if we're looking for some, tangent function? Okay. Well, it ends up that the period relates to b, okay, right? If we know the period, then is what we can do is we can say, well, the period is 3 pi, which should be equal to pi over b for both tangent and cotangent. So if I want to solve this for b, I can. I could multiply both sides by b. And then I could divide both sides by 3 pi. And so pi divided by 3 pi will give me 1/3. So I now have the b in my equation. Let's see if there are any other transformations that have been done here. So for one, you can see these points right here and right here. Normally, those are going to be at 1 and minus 1, but they have been stretched quite a bit. This has been stretched by a factor of 6. So what that tells me is that a is equal to 6. Okay. Now, we do have the question, are there any other transformations? Okay, so I see no vertical shift here because the middle of my tangent function is based along the x-axis here. So there's been no vertical shift. Okay. Maybe I'll arrow to this. No vertical shift. And actually, I'm going to say no vertical or horizontal shift, because also this middle part hasn't been moved left or right. The tangent function, the parent function, goes right through the origin. Okay? And so that origin has not been scooted around. Okay? So yeah, no vertical or horizontal shift. There we go. So that means if that's the case, that means that both C and D are 0. Okay. So when we go to write our final answer here, it should be y equals A. And so our A we said was 6 because we had that vertical stretch by a factor of 6. We're working with tangent. Our B is a third. And then there is no C, so I'm not going to write x minus C. I'm just going to write my x in here. And then there is no D. I don't need to write plus 0 either. So this would be our final answer for this one. So what we have left here is to work with secant and cosecant. And so what I want us to do is we'll go and take a look at those here on the next page. So for secant and cosecant, you're actually going to start off by graphing sine or cosine. Okay. So just as a quick refresher, right, when we're thinking about secant of x, it's really equal to 1 over cosine of x. And if we were to go in and graph cosine here, we know that we want our quarter points to be spaced out by pi over 2s. For the parent function, of course. And I think I'll graph this all the way to 7 pi over 2. Let's do that. And on the other side, I'm going to go to minus pi. There we go. Right, and so for sine and cosine, right, we only have to go up to 1 and down to minus 1. Right, and so if we were going to graph cosine, right, cosine starts at the top of the wave. So I just need to fill all these in here. And so I'm putting this one in yellow because I don't want it to stand out, because this isn't actually the graph of secant. This is about to be the graph of cosine. Right. And I want you to think back to when we were graphing tangent and cotangent. Whenever we had those 1 over zeros, there were asymptotes. Okay. And so the same thing's going to happen here. So now that we're trying to think about secant, we know we're going to do 1 over these yellow values, because these yellow values are the cosine values. And so we're going to wind up with 1 over 0 here, right? Because cosine of minus pi over 2 is 0. So we'll end up with 1 over 0 here. So basically everywhere you see these zeros, we're going to have a vertical asymptote. Okay, so we got all those filled in. Now there are some easy points that we can add in here. So one easy point that we could add in would be at the 1s and minus 1s. So secant should just be 1 over these values that we're looking at. So if you do 1 divided by 1, you actually just get 1. 1 divided by -1, well, you get -1. And so basically, the graphs of secant and cosecant are going to share all these red points that we put in so far. Okay. Now, all the numbers, say, to the right over here or to the left of that peak are smaller than 1. And so if you do 1 divided by a number smaller than 1, you get a number bigger than 1. Okay. And in fact, as we get really close, say to pi over 2, we're going to get 1 over something really small, which is going to give us something really big. Okay. And so we end up getting a shape like this. They're not actually parabolas, but I think it's just easiest to describe them as being parabolic ish. Okay. And so you get all these here, all these U-shaped curves. There we go. So in the red there, the red you're looking at there, that is actually our graph of this is our graph for secant. I'm going to say y equals secant of x. Versus the one in yellow, again, was our graph of cosine. So every time you graph secant by hand, just graph cosine first. Okay. And then it's really easy from there. We're going to do the exact same thing with cosecant. Okay. So I'm going to come down here and let's really quickly add in some of those tick marks, counting again by pi over 2's. I'll just go to 3 pi on this one. There we go. And so this time we're going to graph sine first. And you might remember sine begins at the middle of the wave. And I'll put that middle of the wave in here in just a second. There we go. So here's the middle. Once I select yellow, there we go. And then from the middle, it should then go up if we're moving to the right. And again, we're just going to continue that wave pattern that we make for sine and cosine. There we go. And just like in the last one, we'll get vertical asymptotes whenever we have 1 divided by 0. And you can actually see the zeros on the graphs here. And so it makes it really easy to spot where the vertical asymptotes are going to go. So if we start sketching in here, those U shapes, we will officially have our graph of cosecant. Although mine's looking a little sloppy here. Yeah. And so if we color or put in maybe a little legend here, right, in the red, again, we have y equals cosecant of x, and in the yellow, we have sine of x. Now, this is exactly 2 periods graphed here. It takes one of these downward facing things and one of these upward facing ones to complete one full period. Right? That's the amount of time it takes in order for the pattern to repeat. We have to have 2 of these. That is the pattern, is 2 of them. Same goes for up here. One upward facing one downward facing one is one complete period. So I have 2 examples for us to try here. So example 5 says to graph at least 2 periods of y equals 3/2 plus 1/2 secant of pi x. So I want us to start off by instead thinking about I equals 3/2 plus 1/2 secant of pi x. And is what I'm going to have us do is come up with all the same things that we usually come up with. For instance, 3/2 is our vertical shift. Squeeze that in over here. Vertical shift of 3/2. We could also actually write in the amp. I wrote secant. Okay. I meant to write this in as cosine. I want us to think about 3/2 plus 1/2 cosine of pi x. We're going to graph this yellow function first, and then we'll graph secant. Okay. Now, it also has a vertical stretch of 1/2, or the amplitude. Maybe I'll call it amplitude here since we're talking about cosine. So amplitude is just 1/2. Okay. So this is going to scoot the middle of the wave up 3/2 units, but we're only going to have to go up 1/2 and down 1/2 from that since our amplitude's only 1/2. So let's see if we can maybe put that on here. I think is what I'll do is I'm going to zoom in here for a second, and I'm going to put on here let's see, I want to go all the way up to 3/2 plus 1/2, so that's to 2. Okay. So I'm going to mark that as 2. This will be 1. This will be 3/2, and this will be 1/2. Yeah, let me write those in. Go like that. There we go. All right, so we have the y-axis set up. So is what we could do next is deal with the period and maybe phase shift if we have one. So I want us to write in our period. That should be 2 pi over b. And so b here for us is pi. So the period is 2, which means that the spacing should just be the period over 4, which is just 1/2. So it's going to be pretty convenient spacing on the x-axis. Okay. Now, there is no phase shift. You don't see x plus or minus some number. Okay. So since there's no phase shift, we don't have to think about any horizontal shift. So I'm going to start at the origin, or start at x equals 0, maybe I should say, and start counting by halves. So let's come over here, and we'll start filling those in. Here we are. Okay, I think that should be plenty. Okay. So let's start off there, and I'm going to write in that, again, maybe what we're counting by. We have a -1 here, a 1, a 2, a 3. There we go. And you could write in the minus 1/2, positive 1/2, 3/2, 5/2, 7/2, and so on. But I hope that that's clear that we're counting by halves um, with the way that this is pictured. So now, again, we want to plot the cosine function. So cosine, when you normally plug in x equals 0, you usually get 1. Okay. However, the center of our wave has been scooted up to 3/2. And so the top of the wave will be 1/2 unit higher than that. So starting us up at the top of the wave is actually up here. Okay. And if we're at the top of the wave, we only have one option, and that is we'll have to go down as we move a quarter point to the left or to the right, really. And so again, our amplitude's a half, so I'm just going down a half at a time here. And if I go another quarter point over, I should go down another half, which will bring us to the bottom of the wave. About right here. There we go. And then if I go over to the next quarter point here, I should go back up to the middle of the wave. And then at 2, I should be back up to the top of the wave, which also has a y value of 2. Then at 2.5 here, we should be back down to the middle. Go somewhere in there. And then back down to the bottom. And then back up to the middle. And so let's go ahead and connect with a cosine function. All right. So let's go ahead here and start this process of putting in the asymptotes. So remember, these asymptotes, when we were looking at secant and cosecant, I was saying that these happen at the zeros. Okay. But more specifically, this is the middle of the wave. Okay. And the reason I'm saying that is the middle of the wave for us has been scooted up. Okay. So when we're at the middle of the wave, we will have division by 0, and we can verify that maybe here in a second. Okay. But maybe I'll put in an asymptote here. I'll put in one here. I'll put in another one here. And here. And then there should just be one more after this. This one right here. There we go. So if you're wondering how we are really winding up with division by 0 here, well, maybe let's just consider trying to plug one of these values in. So like this is at x equals 1/2. So if I were to come over here and try to plug in 1/2 into this, let's see what we get. We get y equals 3/2 plus 1/2 secant of pi times 1/2, or pi over 2. Okay. And remember, secant is 1 over the x value on the unit circle. Okay. Well, what is the x value on the unit circle at pi over 2? Okay. Well, it's 0. So we end up with a 1 over 0 here. So this ends up being undefined. Okay. And this is exactly what will happen if you try to plug in any of these other spots where we've sketched in a vertical asymptote. You'll end up with an undefined value. Okay. So now all we have left to do is to make those little U shapes that we were talking about. And so here in the pink, we have the original function, which is that 3/2 plus 1/2 secant of pi x. There we go. All right. And I know that we have a little more than 2 periods because I see 2 sets of these upward and downward facing shapes here. All right. And then lastly, we have a cosecant function that we're going to try to figure out what it is. Okay. So if you have the graph of the cosecant function, you could just sketch in, well, what would the corresponding function look like? Okay. And when I say corresponding, I mean, what will the sine function look like, right? Because sine and cosecant are each other's reciprocals. All right. So the idea is if we can figure out the equation of this orange sine function, then we can figure out the blue function, the cosecant function. Okay. Now, I actually think it's really hard to see here exactly what the amplitude would be, but it looks approximately like a half. Okay. So if you're wondering, is that a third? Is it a fourth? Is it a half? What is it? As long as you're in the ballpark, that's perfectly fine here. But I think it's about a half. Okay. So I'd say 1/2 here, okay, because that's my amplitude. It's how far we're going up off of, or up from the middle of the wave to get to the top. But now another piece here to note is sine usually starts at the middle of the wave. Okay. So we have no phase shift here. And again, maybe I should write in here that is what this is telling me is that A is equal to a half. Okay. So I have A is a half. I also have no vertical shift, right? The center of the wave is on the x-axis. So that tells me for both of these that, well, C is 0 and D is 0. So the only other value we have to look at is B, which is related to the period. Okay. And so if we look at this, it appears that one period is 4 pi units. Okay. Maybe I'll write that in and or write that in more clearly. I'm going to go like this. Okay, so you see one upward and one downward facing shape here. So that's how I know this is one period. But also, if you look at the sine function that we've sketched in, that also seems to have a period of 4 pi. Okay. Let's write that in. Which means, right, that, well, I shouldn't say it means this. The period is also given by 2 pi over b when we're talking about sine and cosine. So is what I'm going to say here is, well, 4 pi is equal to 2 pi over b. And we'll just start solving for b here. We'll have to multiply both sides by b. And then we could divide both sides by 4 pi. And if we do that, that gives us b is equal to a half. So not only was a 1/2, but b is actually also a half. So when we go to write this in here, we would have that 1/2 sine of 1/2 x is the orange function, which means that the one we're looking for in the blue is just simply y equals 1/2 cosecant of 1/2 x. And so basically is what we're seeing here is if you know how to work with sine and cosine, you'll be able to easily graph secant and cosecant. All right, and that wraps up section 5.4.